Okay, so in this video, you'll be learning about the delocalized model of benzene, and this is actually the current model of benzene, and this is actually one of the most amazing pieces of organic chemistry. So many people, when they look at this benzene ring, I mean, they just don't know what's going on. However, if you have some previous knowledge of chemistry, this is pretty simple to come across. So it is proposed by Kathleen Lonsdale, and it is sometimes referred to as a Lonsdale's benzene. Okay, so Lonsdale suggested that a benzene ring actually has a flat planar shape with a delocalized ring in the middle. So if I just zoom into this structure and really focus on how the delocalized ring is formed, well, firstly, the bonds highlighted in yellow. Well, the bonds highlighted in yellow are the sigma bonds. So if I just write it down over here, sigma bonds. Now, if we count how many sigma bonds there are in a benzene molecule, well, let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 sigma bonds in a benzene ring, and each carbon atom forms 3 sigma bonds. Okay, so now we know that each carbon atom actually has 4 valence electrons. But over here we can see 3 bonding electrons, and one of these electrons are unpaired. So this unpaired electron is in this p orbital. So each carbon atom has this p orbital with 1 electron, and this p orbital is actually 90 degrees to the plane of the atom. So you can see there are actually 6 of these p orbitals because there are 6 carbon atoms, so 6 p orbitals, and each of these p orbitals then overlap with the neighboring p orbitals, just like this. So they overlap with the neighboring p orbitals. Okay, so now this overlap is actually referred to as a pi system. Well, it depends on the exam board you're doing, because in OCR A we call it a pi system. However, I believe some books they refer to it as a pi bond as well. So now this overlap actually has 6 delocalized electrons because each p orbital was holding 1 electron. Now they're overlapping, so these 6 delocalized electrons move in a circular motion. These are the 6 electrons. Let's say these are the electrons, these dotted lines moving in a circular motion, and then these are constantly moving randomly, either in the upper lobe or the lower lobe. Now this gives stability to the benzene ring. It allows it to undergo electrophilic substitution, and also this assures that all the bond lengths are actually the same. So now you should be able to compare the delocalized model and the Kekles model of benzene.